Hello everyone, my name is Christos Verginis. I am currently a postdoctoral researcher at UT Austin, and this is a work from my PhD studies at KTH with my PhD advisor, Professor Dimos Dimarogonas, and collaborator Lydia Kavraki from Rice University. The title of this work is Sampling-Based Motion Planning for Uncertain High-Dimensional Systems via Adaptive Control, published in the workshop on the Algorithmic Foundations of Robotics 2020. So this work deals with the motion planning problem for complicated structures, which essentially is to find a way to automatically navigate a system to some desired goal while avoiding obstacles. So, for instance, here in the picture on the right, you see a UR5 manipulator which aims to navigate to the four targets shown here in cubes while avoiding obstacles, which are these rectangular shapes in the workspace. Motion planning has been studied a lot for many years, and there are numerous applications. And maybe the most standard way of doing motion planning for such systems is sampling-based motion planning, which essentially consists of sampling random points in the free space of the robot and trying to connect these points among each other and to the goal in order to create a geometric path for the robot to follow safely to the goal. And it turns out this is very efficient and it scales very well as the number of degrees of freedom increase. So here, for the sequential tasks of navigating to the four targets, we see um, the results of a geometric standard RT algorithm. And we see here the number of nodes for the four sequential tasks and the time taken. And we see actually that in most cases, the algorithm is able to find a path in less than 1 second for the six joints of the robot. One issue, however, is that this is a geometric path, and how can we actually guarantee that the robot will follow safely such a path? And this because of the fact that the robot actually evolves subject to second order dynamics shown here. Um, so Q is the joint vector of the robot consisting of the six joint variables. Q dot is the velocity, and then we have standard inertia, M, Coriolis, C, and gravity terms, G. And Q is the control input, control action of the robot. So in order to take into account such dynamics, there have been kinodynamic algorithms developed, which now instead of just sampling joint space points, they also sample velocity points. So considering the state space of the system, so joints and velocities, and actually by randomly selecting control inputs, they simulate for the system such as these dynamics um, hold in order to see where the system ends up. And in that way, these algorithms create, again, a sequence of points to be followed in the free space, uh, by consisting of joints and velocities. However, such algorithms are actually sometimes very inefficient and they take a lot of time due to the randomized actions and due to the possibly complicated dynamics of the system. So in this case, for just two joints, the first two joints of the robot, the kinodynamic RRT took almost 1,000 seconds to find a feasible path. On top of that, what if the dynamics of the robot are uncertain? So what if these terms here are not known to the algorithm or to the decision maker? The forward simulation of the dynamics can actually fail, or it can produce false trajectories. So motivated by this, we consider in this problem the motion planning in this paper. Sorry, we consider the motion planning problem under Lagrangian robodynamics shown here, where we have also included the disturbance term. In these dynamics, we consider them uncertain or unknown to the algorithm. So M, C, and G, they are unknown, but they we assume they can be parameterized like this. So they can be written as the product of a matrix Y, which is assumed to be known, times a vector theta here, which is unknown. So this theta usually consists of unknown parameters, constant parameters in dynamics, such as mass or moment of inertia. And we also assume that the disturbance here, D, is completely unknown, but uniformly bound. And the goal actually here is to develop a strategy that takes the robot to the goal safely while avoiding the obstacles and at the same time compensating for the uncertainties in dynamics and the unknown disturbances. So our proposed methodology consists actually of two layers. The first layer is a control design, a traditional control design algorithm. So what we do here is we appropriately design the control input U in order to track a given reference trajectory QD. And we aim to do that within given bounds. So shown in the picture here, given these upper and lower bounds, what we want to do is actually to force the system state Q to track the desired trajectory, the reference trajectory QD within these bounds. So here you can see that the error or difference stays in this funnel here formed by the upper and lower bound. Next, we aim to use these bounds in order to create a new extended free space in order to be used in the motion planning algorithm. So here, actually, instead of trying to sample points in the free space of the robot, we sample space in the extended free space of the robot, which takes into account these bounds. So essentially, the output path of the randomized sample-based motion planning needs to be sufficiently far from the obstacles based on the bounds. So here is a nice example in the picture. So given these red obstacles, we sample a path here shown with a solid black line whose distance from the obstacles is more or equal to these bounds that we derived in this in the control design approach. So essentially, what say here is that okay, if the robot actually does not exactly follow this solid line, but evolves in the funnel formed by the dust lines, then the system is still safe. And once we do that, we endow time to this path, time constraints to this path to form a reference trajectory QD, and then we use the control design approach to actually track this trajectory. So the control design layer consists of a standard adaptive backstepping methodology. So we actually first separate the joint and reference trajectories to translational and rotational parts because that's what systems like robotic manipulators consist of. Then we define these errors of the state with respect to desired trajectories, which we want to converge to zero. We want to force these errors to zero. And the idea here is to design a reference velocity, here denoted by alpha, which we would like the robot to have. And this is actually a very standard proportional feedback controller. So it consists of the velocity of the desired trajectory minus a gain, a positive matrix gain times this error. And this is for the translational part. It's actually equivalent. The rotational part is is similar. It's just that we use these cosines and sines because we take into account the fact that rotational joints evolve in manifolds. But these two expressions are equivalent. So once we have defined these reference velocities, we formulate the respective error, which is the actual velocity of the robot minus the reference velocity. And since we would like the robot to have the reference velocity as velocity, we want this error to also converge to zero. The second step consists of the actual design of the control input. So as a reminder, the dynamics part here is factorized uh, subject to this form. So the product of a known matrix y times a constant but unknown vector theta. And since this theta is unknown, we use an estimate algorithm, theta hat. And that adaptive control law actually consists of three terms. So these three terms are shown here. The first term is this y known matrix times the estimate of theta. This y matrix is evaluated with reference velocities and accelerations that we designed in the previous slide. And this first term actually tries to compensate for the uncertainties in the dynamics. For this first part of the dynamics over here, and the rest of the terms are just error proportional and derivative error terms. So EV is the velocity error we defined before, and the EX is actually a position error shown here. It just looks weird because as said before, we have the rotational joints which evolve in manifolds. And this KV here is again a positive constant gain matrix. Of course, since we have the parameter estimated hat, we need to describe how it evolves over time, and this is done by the second equation here. So it's the derivative of the estimate, and it's actually similar to a gradient algorithm. So it's minus this regression matrix times the error minus the theta hat itself. And we use again constant gains like gamma and sigma theta, positive gains, and lambda mean here denotes the minimum eigenvalue from this matrix. So by using this adaptive control law, we can actually show that the state evolves close to the desired reference trajectory to D, in the sense that the error is bounded by some bound delta. And this bound actually depends on the bound of the unknown uncertainty and also on the bounds of the dynamic terms. And we can use this delta to, as described before, to form the extended free space. So the extended free space is essentially the space where the inflated volume of the robot does not meet the obstacles, and this inflated volume of the robot is essentially the original volume inflated by these delta bounds. So here on the right, we have an example. So in the original RRT, here this is the line or the path we would produce, and if the robot manages to follow this path, of course, it is safe. However, in our new algorithm, we cannot exactly track the given path or the given trajectory, so we need to create the extended free space defined by delta here, which essentially says that okay, the robot needs to be safe even if it tracks the path out with in this funnel. So given these bounds here formed by the dashed lines. So once we get such a path in the new variant, the new extended, let's say RRT, we can use the control design of the previous slides to actually track this path. So we verified the results with VREP computer simulation. So in the environment VREP, we used this standard example of UR5 consisting of 6 joints, which we assume to be rotational joints. And the robot, as stated before, needs to visit sequentially the 4 targets. So target here, target 2, target 3, target 4. We assumed that the extended free space was formed with 0.1 radians as a final constraint. And since actually we cannot form a proper distance metric for the whole manipulator, in order to check the feasibility of the extended free space, we simply check a number of points here denoted by Z in order to see if the extended free space, if the extended space is actually safe. And what we do essentially is we compare the complexity of our algorithm with a standard geometric RT and the kinodynamic RT, and we evaluate the design feedback control law. So these are the results of our algorithm. So here in these the middle and right tables, we see the results where we use 10 points and 50 points in the extended space to evaluate whether it's collision free or not. And we can see here that actually the time taken is usually low, definitely compared to the kinodynamic RFT, which actually involves the dynamics. Um, in our algorithm, we see that the number of nodes is similar to the geometric RT. The time taken is greater, of course, because we look in the extended we look in the extended free space. We sample more points, so in this case 10, and in this case 15. Of course, in this case we take more time. However, we stress here that the proposed algorithm, the proposed motion planning in the extended free space is completely decoupled from the dynamics. The dynamics are taken into account by the proposed control design. So actually, in this way, we can do motion planning very efficiently in the geometric space at the same time by taking into account implicitly the dynamics through the control design. And this is what makes this algorithm very efficient. And this is a video of the manipulator actually navigating up to the 4 points safely in the VREP environment. And this is a plot of the trajectory errors. So this is the signals of the state minus the desired reference trajectory, so Q minus QD. And since we have 6 joints, we have actually 6 signals here. And the important thing to notice here is that they always remain inside the funnel minus 0.1, 0.1. Remember that we used as delta as bounds for the extended free space, delta equals 0.1. And this is actually the evaluation of the control of the feedback control law. Is actually we actually show that the application of this control law keeps the system in the desired funnel, which of course means that the system will be safe. So to conclude, this paper consisted the motion planning problem of complex robotic structures like robotic manipulators. We integrated sampling-based motion planning techniques with adaptive control. So we designed first a traditional adaptive backstepping controller that takes into account and compensates for the uncertainties, for the uncertain dynamics. And then we use that in the motion planning algorithm to develop an efficient geometric way of navigating or creating a safe path to the goal, while at the same time without involving the dynamics which are implicitly taken into account by the control design. So possible extensions are actual physical experiments on this framework and extensions to non-holonomic or underactuated systems such as underwater manipulator systems. And another extension would be to be able to use a priori bounds or user-defined bounds for the extended free space and have them not defined, not based on the bounds of the uncertainties or the disturbances. Thank you for your time.